Alright, so now for the second lecture, we're going to talk about sets. The assumption is that you've already seen a fair bit of set theory before. We aren't going to turn this into a course on set theory, so it's okay if they're a little bit informal here, but the goal is to review the key concepts and the concepts that will be helpful for us for our abstract algebra in particular. So informally, we might say that a set is a collection of unique objects. Now, there's a couple things that aren't 100% accurate with this definition that I gave informally. So, I want to make sure to make note of them first. If you have a set that does not have unique objects, the set 1, 1, 1, 2 maybe, this is the same set as if we just say 1, 2. So when we write a set, we typically don't repeat elements, we only consider the elements that are unique. However, if you have a set written without unique elements, that doesn't mean it's not a set, it's just not fully simplified. The second piece here that I'm not going to go into a lot of depth with is there are certain ways that you can come up with weird paradoxes, such as Russell's paradox for sets. So we're going to operate under the assumption that these things are non-contradictory. For our abstract algebra course, we're mainly dealing with finite sets. We might occasionally come across something like a set of real numbers, set of complex numbers that's not finite, but all the sets we'll be dealing with are nice enough to where we don't have to worry about weird quirks like Russell's paradox. But if you study these things deeply, you will see certain quirks like this that this definition that I gave informally does not apply, or does not address. So, great. If we think of sets, there are a collection of objects. I didn't really say what these objects are. These objects could be numbers, they could be shapes, they could be other sets. You kind of got a lot of flexibility. They can be finite, they can be infinite. So I could do a set like 1, 2, 3, keep it going forever. That's your set of natural numbers without zero. You could do a set of different shapes, triangle, circle, oblong, blob, squiggle, blob. You could do a set containing 0, the set containing 0, the set containing the set containing 0, and so on. You really have a fair bit of flexibility with these things. So we're going to often write sets using set builder notation. It's kind of a pain to write out every single element of a set explicitly. So oftentimes you'll see some notation like this: the set containing all x such that x is a real number and x is greater than or equal to 0. And this is the same as if we were to write out an interval notation, this right here. So you'll see a bar typically for such that. Sometimes you'll see a colon, sometimes you'll see st, but typically it's a bar or a colon. It kind of depends on the text. We'll use a bar for our course. Notice we're saying, here's the thing we're putting in the set, and then here's the rules governing that thing. So if I just said the set containing x such that x is greater than or equal to 0, that's not good enough. I'm not saying where x is coming from. I need to specify whether x is a natural number, real number, rational number, whatever it might be. Now, the other things we like about sets is we like to be able to do operations on sets. We like to be able to combine them in different ways. We like to be able to pull out specific members of sets. So let's go ahead and review some of the notation for those kinds of things. For our set, we might say x is an element of set A. X is an element of set A is what this means. Or you might say this more informally as x is in A. So for example, if we have the set of A equals 0, 1, 2, then it would make sense for us to say 1 is an element of A, right? because we know 1 is inside of this set right here. Likewise, you might say x not in A, or x is not an element of A. Okay. This notation is pretty standard throughout math, right? Line just means negation. That's not the case. So we would say 3 is not an element of A if we're using this same set A up here, 0, 1, 2. Now, some other things you might care about with sets. The set containing no elements, some people write like this. We're going to write it like this with a line through it. This is called the empty set. And as a definition, the empty set is the set containing no elements. And the empty set, we can say x is not an element of the empty set for all x. It doesn't really matter what x is. We know the empty set has no elements, so this is clearly going to be true. You can't say anything's inside the empty set. Now, we have these sets, the empty set, and we have A, so maybe we'll talk about some operations. Within sets, you've got two main operations that everything kind of builds on. You've got union and intersection. So what union is going to do is we're going to say A union B is equal to the set containing all x such that x is an element of A or x is an element of B. So for example, if we use the same A as before, 0, 1, 2, and we use B to be 2, 3, 4, then we might note that A union B is going to be 0, 1, 2, 3, 4, because each one of these members is a part of A or part of B. 0 is in A, 1 is in A, 2 is in both A and B, 3 is in B, 4 is in B. Intersection, on the other hand, we would say A intersection B is equal to the set containing all x such that x is in A and x is in B. So in this case, we only have one element that's in both sets, namely 2. So our intersection is going to be the set with only a 2. So we do get a few extra definitions out of this for free, or relatively easily. So we might say two sets are disjoint if their intersection is the empty set. So for example, if we were to take A to be equal to the same A we had before, and this time what if we define a new set C which is equal to 6, 7, 8? Then we would say that A intersection C is equal to the empty set because there's no members of A that are also in C. There's no members of C that are also in A. So we would then say thus A and C are disjoint. Now, one thing we've kind of assumed implicitly here that I want to make sure we're very clear on is we've kind of glossed over what it means for two sets to be equal. We said A intersection C is equal to the empty set. Previously we said equality when we performed these operations of union and intersection. So what we mean when we say two sets are equal is we mean that two sets share all of the same elements. And with finite sets, it's pretty easy to check element by element. You can check them both off of your checklist and compare them. But when you get to infinite sets, it's not quite as easy to do so always. So in order to get to a notion of equality that's also well defined for infinite sets, we first need to make sure we understand subsets. So first we would say a set A is a subset of B, specifically set B, if for all elements of A, these elements are also going to be inside of B. So for example, we might say if A is equal to the set 0, 1, 2, B is equal to the set 0, 1, 2, 5, 7, 9. A is a subset of B. This is a symbol used for subset. Now, this is true because 0, 1, and 2 are all elements of B. Now, what we're going to note here is B is not a subset of A, as 5 is not an element of A. And for this class, this right here is going to be the symbol for subset. Note that by this definition, A is a subset of itself because every element of A is also an element of A. And we can also note that the other way around is true as well, right? You can write it the opposite way, kind of like you can with a greater than or equal to sign. So if we want to say two sets are equal, then we would assume that both of these things must be true. So if two sets are subsets of each other, we'd say they're equal. Now, a couple more notes about notation I want to make sure we're clear on. Some texts will use this right here to be subset. Some texts will use this to mean strict subset. And what we mean by strict subset is we mean that A is a subset of B and A is not equal to B. Now, to be honest with you, because some people use this to mean subset, some people use it to mean strict subset, and it's not always clear which one unless you get the context. I'm going to be very specific when I mean strict subset in this class. This right here is what we will use for strict subset. It's a little bit annoying having to write a slightly more complicated symbol, but I don't want any ambiguity, where if I use the strict subset as the subset symbol without the line, then that's going to lead to ambiguity. It's just a quirk of the notation, unfortunately. So, other than that, I just want to make note of the fact that the empty set is a subset of A for all A. It doesn't matter whatever set A is, this is always true. And why is this true? Well, it's vacuously true because every element of the empty set is also an element of A. The empty set contains no elements, so when we say every element of the empty set, doesn't particularly matter what A is because it's vacuously true. There are no elements, so it's just true automatically. You get that one for free. So beyond this, we have our notion of equality of sets. We have our notion of subsets. We have our notion of something being included. We have union, we have intersection. The other pieces that we really care about, we care about symmetric difference, we care about Cartesian products, and that'll take through most of what we need to know for sets for this course. So what do we mean by symmetric difference between sets? Well, we gotta be careful what we mean by any kind of difference between sets, because there's really two different notions of difference we can use. If we're talking about symmetric difference, it's kind of special because we're assuming that it's the elements that are in one set or the other set, but not both. It's like an exclusive OR. And the symbol we will use for symmetric difference in this course is we will use the symbol, this plus with the circle. So you can write this a couple different ways. You could write this as A union B minus A intersection B. More on what this minus means in a second. Or you could say the set containing all x such that x is an element of A or x is an element of B and x is not an element of A intersection B. If we're thinking about a Venn diagram, that's the easiest way to think about this. Here's A, here's B. Our symmetric difference is all this stuff. I guess if we were to go back to union and intersection, it might be good to draw a Venn diagram as well. So if we're thinking about union over here, our Venn diagram is going to look something like this. Here's A, here's B. We care about the entirety of both circles. For our intersection, we might say here's A, here's B. We only care about the overlapping region. So if that's symmetric difference, what do we mean by regular difference? What do we mean by A minus B? Because I did use that implicitly above. Well, this is going to be equal to the set containing all x such that x is an element of A and x is not an element of B. This one is not symmetric, right? Because it is possible that B is a subset of A, for example, and A without B could be non-empty, but then if we take B minus A, then it would be empty. Also note that if B contains elements not in A, you don't really worry about those ones. You only worry about the stuff in A and remove things from A. So you might note that this right here is always a subset of A, but we don't really have any claims about the way this relates to B beyond the fact that no member of B can be here. Right, so we know B and A without B are disjoint. Now, another notion we might get out of this is we might also get complement. So suppose we have the big set X, right? The universal set X. What we mean by the universal set is we mean the place where all of these sets live. So for a set X with subset A bar, which we would call a complement, is the set containing all elements of X that are not in A. So honestly, writing this out as words, probably not the most helpful way to do this. The easiest way to see this is in set builder notation. We take X minus A, and if we remember our difference definition above, you can see that as well. If we're thinking about this in terms of Venn diagrams, we might say, here's our set A. This whole shaded region here is going to be a complement, and then this entire rectangle might be X. If we go up here to regular difference, we might want to show this one as well. Here's A, here's B. We're taking all the parts of A that do not overlap B. So I guess with difference, we might want to do this in terms of union and intersection as well. We're taking I think set builder notation is fine, actually, sorry. You could do this in terms of union and intersection as well, but then you still want that difference, and if you can accept this right here, x is element of A and x is not element of B, then you can use union, intersection, and difference to define many sets. So now that we've got the notion of complement, we might make note of what it means for something to be a partition. For a set X, a partition P of X is a collection of sets A sub I such that the union for all the i's here is equal to X, and each pair A sub I, A sub j is disjoint for I not equal to j. So basically what you're doing is you're taking your region X and you're chopping it up into different sets. They don't necessarily have to be the same size or the same shape. This might be A1, A2, A3, A4, A5, A6. And I also want to note that these don't necessarily have to be finite sets either. So for example, if I want to partition X, which is equal to 0, 1, 2, 3, 4, I might say A1 equals 0, 1, A2 equals 2, 3, 4. And in this case, note that A1 union A2, you get back the original set X because you got 0 and 1 in A1, 2, 3, and 4 in A2. And then A1 intersection A2 is equal to the empty set. We will do one more example of a partition. Suppose we have X being equal to all the real numbers, and we say that A1 is equal to the set 0 to 1, A2 is equal to the set negative 1 to 0, A3 is equal to the set 1 to 2, A4 is equal to the set negative 2 to negative 1, and we're just going to keep going back and forth forever. And we're going to also add one additional set I'm going to call A0, and A0 is equal to all of the integers. I claim the union from I equals 0 to infinity of all of these A sub i's should be equal to the real numbers. And this makes sense because if we're drawing out what these sets look like, we're imagining we get something like this, where each one of these regions between the holes is an interval that's included as a set. And then you get your net integers, which is going to be where all these holes are as well. Now, what about the partitions? Well, each one of these intervals is disjoint, right? They never overlap with each other. And furthermore, none of these contain an integer inside of them because the integers are the endpoints, which are not included. These are open intervals. So we would say these sets are disjoint as well. So we'll consider both cases. Case 1, A0 intersection with AI for I being greater than 0 is equal to the empty set as each interval does not contain any integers, right? Case 2, A sub I intersection A sub j is also equal to the empty set for I, j both being greater than 0 and I not equaling j, as we note that these intervals do not overlap at all. Therefore, we have a partition. The last piece of information I'd like to go over briefly is the Cartesian product. So we're going to be a little bit informal here. If you're taking a course on set theory, you might talk about how to define ordered pairs and the like. But for our purposes, we're going to assume you're familiar with ordered pairs, right? With the set, we don't care about the order of the elements. We know that 0, 1, 2 is the same thing as 2, 0, 1 in sets, right? But in ordered pairs, ordered triplets, ordered however many elements you have, these two things are not necessarily equal, right? Because the order matters now. So when we're getting Cartesian products, it's kind of allowing us to define our ordered pairs, ordered triplets, ordered n-tuples, however many elements you got. And the way you do these things is you'd say A Cartesian B is equal to the set containing all A, B, such that A is an element of A and B is an element of B. So this multiplication symbol might seem a little strange at first, but the way I like to conceptualize this is if we have a set like A, and maybe A is equal to 0, 1, 2, if we have a set B, maybe these ones are letters, A, B, C, then what we can do is we can imagine making a grid. 0, 1, 2, and then A, B, C. And what we're doing is we're pairing these things off, right? We said A first, B second, and you know what I'm going to do? I'm going to change this slightly. I'd like to instead draw this in a slightly different order. Darn it, it keeps erasing when I don't want it to. Okay, let's try this one last time. Okay. Now we've resolved that. Let's try one more time. What I was trying to do instead is I want to make sure I'm putting A on the left side here, B up top. So if we fix the convention, we've got 0, 1, 2 like this. We've got A, B, C up top. So we could say we have 0A, 1A, 2A, 0B, 1B, 2B, 0C, 1C, 2C. Notice we're pairing these things up. And if we're thinking about multiplication, you could think of it more analogous to a multiplication table than you would think of it as multiplying two numbers to get another number out. It's more the pairing part going on. And this notion is particularly helpful to us when we start talking about binary relations and equivalence relations, which we will start on soon enough. That's all I've got. I will leave you with some problems in the next video.